It's 2 a.m. Your coffee is completely cold.
Yep, we've all been there.
The glow of your IDE is, lighting up the whole room, and you're staring at an API endpoint that just will not behave.
It's the classic late-night developer reality.
Exactly. And if you are a software engineer who's just trying to cut through like the massive wall of AI hype right now.
Oh, the hype is everywhere.
It's exhausting. But if you want to understand the actual literal mechanics of modern AI architecture, you are in the exact right place.
Today, we are doing a deep dive into a really fundamental shift in how we build applications.
Yeah, we're looking at a framework called ReAct, that's spelled R-E-A-C-T, which stands for reasoning and acting together.
Right, because, we all know large language models can output a decent Python script or, summarize a meeting transcript. That's table stakes now.
Totally.
But getting them to actually execute tasks in the real world, like querying a live production database or restarting a server or, booking a flight, that requires a completely different approach. It does. The transition from a model that just generates text to a model that actually functions as an autonomous agent is basically the defining engineering challenge right now.
Yeah.
And if you are building software today, you really don't need another high-level think piece. You need to know how the gears actually turn.
Right, how the architecture is actually structured.
Exactly. And perhaps most importantly, what the failure modes are when you actually try to deploy this stuff into production.
So to see why ReAct is such a massive leap, we first have to look at, the corner we kind of painted ourselves into with standard language models.
Yeah, historically, we've forced these models down one of two very isolated paths.
Right.
The first path is what we can call pure reasoning. This is, your classic chatbot interaction. You give the model a complex logic puzzle or ask it to draft a system architecture document.
It's great at that.
It is. It's incredibly powerful at synthesizing information, parsing language, generating structured responses, but it suffers from a fatal flaw.
Which is that it's entirely limited to whatever was in its static training data.
Exactly. Or, whatever context you manually pasted into the prompt.
Yeah.
It's frozen in time. It's totally disconnected from the live state of the world.
I always think of this pure reasoning approach like having a brilliant, world-class philosopher locked in a windowless room.
Oh, that's a great analogy.
Right. Like, they have memorized every encyclopedia up to last year.
Yeah.
You can slide a piece of paper under the door with a complex ethical dilemma, and they'll slide back just a masterpiece of an essay.
Yeah.
But if you slide a note under the door asking, hey, is it raining outside right now? They have absolutely no idea. They literally cannot look out a window.
Right, which naturally led developers to try and solve that isolation by building systems for the second path, which is pure acting.
Pure acting.
Yeah. We started mapping specific user intents directly to specific APIs. Like, if the user types a sentence containing the word weather, a script just triggers the weather API and returns the result.
But pure acting lacks deep planning, right?
Yeah.
It's essentially just a reflex.
Exactly. It doesn't synthesize or strategize at all.
Because if you ask a pure acting system, based on the weather in Seattle and the current traffic on I-5, should I leave now to make a 3 p.m. flight? That reflex just completely breaks down.
It does.
It might trigger the weather API, but it can't, sequence the output of that API into the input of a traffic API and then evaluate those results against a time deadline to formulate a recommendation. It has hands, basically, but no brain.
And that is exactly where ReAct comes in. It bridges that gap. It combines chain-of-thought reasoning with dynamic external tool use.
Okay, so how does it actually do that?
It creates a structured, iterative state machine, which is defined by this core loop: thought, action, observation.
Thought, action, observation.
Yeah. Instead of just trying to generate a final answer in one single shot, the model is prompted to think aloud, take an action, observe the result, and then reevaluate.
Let's map that onto the Seattle airport scenario. What does that actually look like in the literal prompt sequence?
Okay, so you give the model the complex task. Should I leave for my 3 p.m. flight now? Step one is the thought.
Okay.
The model internally reasons about its immediate requirement. It generates a literal string of text that says, thought, I need to find the current weather in Seattle to determine if driving conditions are impacted.
Wow, so it actually prints that out.
Yep. Then step two is the action. Based on that thought, it outputs a command to use a specific external tool, something like Action Weather API, Action Input Seattle.
And this is where the external environment comes in, right?
Yep.
Step 3 is the observation.
Exactly.
The external tool returns actual data pouring rain. And the model observes it.
Then the loop repeats.
Yeah.
The model evaluates that new observation and generates a new thought. Since it's raining heavily, traffic will be slower than usual. I should check the traffic API for I-5.
Right.
It takes a new action, observes the new result, and just continues iterating until it has enough context to provide a final, reasoned answer to the user.
But here's where I feel like the theory hits a wall in practice. Standard LLMs are notorious for just spewing out a giant wall of text all at once.
Oh, absolutely.
They just want to predict the next token continuously until they hit an end of message token. So how do you stop the LLM from just hallucinating an answer before it even waits for the tool result?
That's the big question.
Because, I mean, we can't just politely ask the model to pause its text generation, wait a few seconds for a network request to resolve, and then pick up where it left off.
No, you can't. And the solution to that is the fundamental secret of this entire paradigm. The language model itself does not run the tools.
Right.
The model is completely incapable of executing Python code or making an HTTP request. It is simply a text prediction engine.
Yeah.
To make the ReAct loop function, developers have to build a robust external wrapper around the model. We call this the orchestration layer.
The orchestration layer, which means the model is really just generating text that's formatted as a command, and we, the developers, have to catch that text, parse it, run the actual code, and feed the results back.
Yes, you hit the nail on the head. We are building the runtime environment for the brain.
I love that.
This orchestration layer is a piece of software written in Python, TypeScript, Go, whatever your backend stack is, that sits right between the user and the LLM API. And this layer has three critical jobs: intercepting, executing, and injecting.
Okay, let's dive into the actual mechanics of that. Intercepting. If the model is just streaming tokens back to us, intercepting must mean we're evaluating those tokens on the fly, right? Looking for a specific trigger to halt the generation.
Exactly. It comes down to utilizing stop sequences.
Stop sequences.
Yeah, when you send the initial system prompt to the LLM, you include a specific stop sequence parameter in your API call. Often, it's literally just the string observation with a colon.
Okay.
So the model begins generating text, thought, I need the weather, action weather API, action input Seattle. Then, the exact moment the model tries to predict the word observation, the LLM's API terminates the generation.
Wait, really? It just cuts it off?
It forcefully halts the model and returns the payload to your orchestration layer right then and there.
That is incredibly elegant. The LLM is essentially shouting out, hey, somebody run the weather tool. And our orchestration layer says, got it, stopping you right there. That's the intercept phase.
Perfectly stated. Then comes the executing phase. Your Python script parses that intercepted text. It extracts the tool name, weather API, and the parameter Seattle.
Yeah.
Then your script makes the actual HTTP request to the external weather service.
And this is a vital security boundary, too. I mean, an API call requires authentication headers, secure connections, environment variables. We absolutely do not want a non-deterministic language model holding our production database passwords.
Never.
Or trying to, dynamically construct SQL queries with full write access. That's a nightmare. The orchestration layer ensures that the LLM only requests an action, while the developer's deterministic code handles the secure execution of that action.
That boundary is so critical for production safety. So once your secure execution completes, the API returns a payload, say, a JSON object, containing temperature, precipitation, wind speed.
Right.
This brings us to the third job, injecting. Your orchestration layer takes that JSON payload, formats it as text, and appends it to the ongoing conversation transcript.
So it basically writes the next line for the model.
Exactly. It literally writes, observation, the weather is 45 degrees and raining. Then, it sends that entire updated transcript back to the LLM API, prompting it to continue generating the very next thought.
But wait, injecting isn't just blindly pasting data, is it? Because we run into strict infrastructure constraints here, specifically the context window limit.
Oh, big time.
You can't just take a 10-megabyte JSON response from an enterprise database and dump the raw output back into the prompt. It will instantly blow up the token limit and the model will just crash.
Managing the context window is a major part of the injecting phase. A sophisticated orchestration layer doesn't just pass raw data, it parses and truncates it.
Right, it sanitizes it.
Yeah, if you query a database for user records, your Python code might need to extract just the 5 relevant fields from a massive JSON object, format them into a concise string, and inject just that into the observation.
Because you're basically constantly curating the scratchpad of the model so it retains a necessary state, without forgetting its original instructions due to token overflow.
Exactly. It's a complete shift in system design.
Oh.
We aren't just writing root applications anymore, and we aren't just doing basic prompt engineering either.
No, we are engineering a stateful loop. We're building a state machine where the LLM is the non-deterministic decision engine. But our traditional code is managing the state, handling the security, doing all the heavy lifting in the real world.
You are curating the environment that the AI operates within. You're giving that philosopher in the windowless room a very specific set of buttons they can press, and you're acting as the intermediary, securely sliding the results back under the door.
I love that. But because we are talking about building actual software for real users, we have to talk about what happens when things go wrong.
And they will go wrong.
Right. A clean thought-action observation loop works beautifully in a sandbox, but production environments are messy. APIs time out, databases return null values, and, the model itself can make really poor decisions.
Putting ReAct agents into the wild exposes several very specific failure modes. The first, and honestly most expensive, is the loop trap.
The loop trap. That sounds like a classic infinite while loop, but vastly more dangerous because every iteration is hitting a paid LLM API endpoint.
That is the exact risk. Imagine the model thinks, I need to check the inventory database for item 402. It outputs the action. Your orchestration layer executes it, but the database returns an error, maybe a 404, or maybe the item ID was supposed to be a string instead of an integer.
Oh, I see where this is going.
Yeah, your layer injects that observation back. Observation error, record not found. The model analyzes this and thinks, that didn't work, I will try again. And it outputs the exact same action with the exact same parameters.
And it just sits there, stubbornly slamming its head against the wall, firing off identical broken API calls, burning through your API credits by the second.
Yes, it lacks the human intuition to immediately realize a system is down and pivot to a different strategy.
So how do we fix that?
To prevent this, the engineering solution relies on strict state management within your orchestration layer. You have to hard code a step limit.
Like a max iterations counter.
Exactly. You introduce a max steps variable, say set to 5. Your Python script tracks every iteration of the loop. If the agent takes more than 5 steps without returning a final formatted answer to the user, the orchestration layer just kills the loop.
It throws an exception.
Right, it kills it, throws an exception, and returns a graceful error message to the client.
Good old-fashioned timeout logic. You simply cannot trust an LLM to reliably break its own infinite loops.
And ever.
What's the next major failure mode developers hit?
Tool selection errors. This happens when your agent has access to a wide array of tools, maybe an internal wiki search, a customer database query, and a public web search. The model simply picks the wrong tool for the job, or it hallucinates a parameter that the tool doesn't even accept.
If the model is picking the wrong tool, how do we fix that? Do we adjust the system prompt, or is it like a routing issue?
It requires a fundamental shift in how we think about documentation. To fix tool selection errors, you have to write clear, highly structured API documentation, but you are writing it explicitly for the AI, not for a human developer.
Wow. That is a wild concept to wrap your head around. We literally have to optimize our doc strings and API specifications for a neural network's reading comprehension.
Yes, exactly. In the system prompt, you define the tools available to the model, usually as a JSON array. If your description simply says tool searches the database, the model might try to use it to search for general knowledge, like, the capital of France.
Which would fail.
Right. You have to write exhaustive defensive descriptions, like search tool only. Use this to search the internal company database for employee records. Requires a 5-digit employee ID integer. Do not use this for public web searches.
We are essentially treating the AI like an incredibly literal junior developer who just doesn't understand the company architecture yet.
That's a perfect way to look at it.
We have to leave overly explicit comments and guardrails directly in the tool definition so it understands its boundaries.
And even with perfect documentation, you will still run into the third major failure mode, compounding mistakes.
Compounding mistakes.
Yeah, in a multi-step ReAct loop, early errors basically poison the rest of the chain. If the model pulls the wrong customer ID in step 1, and then uses that incorrect ID to query billing history in step 2, by step 5, its final reasoning is completely detached from reality.
Because if step 1 pulls bad data, the entire context window becomes corrupted.
Exactly.
So how do we build resilience against that? How do we stop the compounding mistakes?
The fix is robust error handling injected directly into the prompt. When a tool execution fails in your Python script, you don't just return a generic observation error.
Okay.
You inject the actual stack trace, or the specific API rejection reason, back into the observation. You return Observation API rejected the call because employed must be an integer, but you provided a string 5. Please correct the formatting and try again.
So you are literally teaching the model how to debug its own syntax errors on the fly.
Yes.
By passing the descriptive error back into the scratchpad, the LLM can read the stack trace, reason about why its previous action failed, and formulate a corrected action for the next iteration.
It's incredibly powerful. By mastering these architectural patterns, step limits, AI-optimized documentation, and prompt-injected error handling, you elevate a fragile language model into a highly reliable, autonomous agent.
Which is the whole goal.
Right. ReAct is the foundational blueprint. Any system you see today that perceives an environment, reasons about it, takes an action, and iterates based on the result is built on these exact mechanics.
But fixing failures and building a stable React loop is just the baseline, isn't it?
Oh, absolutely. It's just the start.
Because once you have a single reliable agent that can use tools, you hit a new ceiling. Complex reasoning. Like if a single agent gets stuck on an incredibly difficult logic problem or a highly ambiguous task, how do we scale that intelligence? We can't just make the loop run longer.
No, you can't. And that brings us to the next evolution of agent architecture. When a single ReAct loop isn't enough, we look to a technique called self-consistency.
Self-consistency. Okay, how does that build on the foundational loop we just spent all this time constructing?
Think about human problem solving. If you are handed a critical, complex engineering problem, you don't just blindly follow the very first train of thought that pops into your head.
Right.
You brainstorm multiple different approaches, weigh the outcomes, and choose the path that yields the most logical result.
Yeah, I'll sketch out a database migration strategy, but I'll also sketch out a parallel processing strategy and then compare them. ReAct, in its basic form, is really just following a single linear chain of thought.
Exactly. It's one detective investigating a case step by step.
Okay, so self-consistency is what, hiring more detectives?
Basically, yes.
Mm-hmm.
Self-consistency scales that detective work by parallelizing the reasoning process. Instead of orchestrating one ReAct loop, your backend spins up multiple independent ReAct loops simultaneously, all tackling the exact same user prompt.
So the orchestration layer is firing off 5 separate API calls to the LLM at the exact same time.
Yep.
But wait, if they all receive the exact same prompt, won't they just return the exact same thought action observation sequence?
Not if you adjust the model's temperature.
Ah, temperature.
Yeah. Temperature is the parameter that controls randomness and token prediction.
Yeah.
Temperature of 0 means the model is purely deterministic. It will always pick the most mathematically likely next word. But if you crank the temperature slightly higher, you introduce entropy. The model might pick the second or third most likely word.
Which means the 5 parallel loops will naturally diverge.
Precisely.
One chain might decide that checking the customer database is the best first step. Another chain might decide to query the billing API first. They each go down completely independent thought action observation paths using different tools in completely different sequences.
It's like moving from one brilliant detective to orchestrating an entire precinct of independent investigators.
I love that.
And the crucial mechanism happens at the very end. Once all 5 parallel loops reach a final answer, the orchestration layer evaluates the outputs. It essentially asks the detectives to compare notes.
Okay.
The software uses a voting mechanism to find the consensus.
But how do you evaluate that programmatically? Like if one model outputs the integer 42, another outputs the string 42, and another outputs a full sentence saying the answer is 42. A simple, exact match script would say they all disagree.
That is a great point. That's where you implement semantic similarity evaluation, or sometimes even use a smaller, faster LLM purely as a judge to evaluate the 5 answers.
Oh, so you have an AI judging the AI precinct.
Exactly.
Yep.
If the judge determines that 4 out of the 5 parallel chains arrived at the exact same logical conclusion, despite taking completely different investigative paths and utilizing different tools, you can have mathematically high confidence in that result.
That is a staggering paradigm shift in system design. We are no longer just sending prompts and receiving text. We are managing fleets of reasoning engines. We are orchestrating consensus.
You are building distributed systems where the nodes are individual AI agents. It completely redefines what a software architecture can even look like.
Wow. Let's bring all of these concepts together for the listener. The goal was to understand how we get language models to actually execute tasks in the real world. And the blueprint is ReAct.
Yes.
It is the vital bridge between static text generation and dynamic action, allowing a model to reason and use tools through that thought action observation loop.
And making it function requires the orchestration layer. Software engineers have to build the infrastructure that intercepts the model's text generation via stop sequences, securely executes the requested APIs, manages those context window limits, and injects the observations back into the prompt.
Right. And you manage the chaos of production by enforcing step limits to prevent those infinite loop traps.
Very important.
You inject stack traces to prevent compounding mistakes, and you write hyper-specific tool documentation so the AI knows exactly what levers it can and cannot pull.
Exactly.
And once you master all that, you can scale it up with self-consistency, running parallel loops to achieve high-confidence consensus on complex problems. It is just a wildly exciting time to be writing code.
It really is. The transition from static code to agentic architecture is fundamentally changing the role of the developer.
But before we sign off, I want to leave you with a concept to mull over while you stare at your IDE tonight. We've talked deeply about how ReAct allows a model to use the tools that you, the developer, build for it through an orchestration layer. And we've explored how self-consistency allows multiple models to debate the best path forward. So, how long until these agent panels start writing and testing their own tools on the fly?
Well, man.
Right. If an agent gets stuck and realizes the tool it needs doesn't exist, how long until it dynamically writes the Python script for a new tool, tests it, and patches it directly into the very orchestration layer you were supposed to build for it?
It raises a profound question about where the boundaries of software engineering will actually settle when the scaffolding itself becomes dynamic.
It really does. Just something to keep you awake a little bit longer tonight. Thank you so much for joining us on this late night deep dive. Keep building, keep experimenting, and we'll catch you on the next one.